For decades, we have gazed into the cosmic abyss with a single burning question: just how far can humanity actually go before the void breaks us? While the universe is infinite, our bodies are fragile vessels tethered to Earth by gravity, radiation, and the tyranny of time. However, groundbreaking new data has finally revealed the hard limits of our reach, challenging everything we thought we knew about interstellar travel. From nuclear engines that scream through the silence to hibernation technologies that cheat to death itself, we are about to uncover the specific innovations that will either carry us to the stars or leave us drifting in the dark. The calculations are in, and the true limit of human exploration is far more shocking than you ever imagined. The moment the main engines cut off and the spacecraft enters orbit, the human body begins a radical and immediate transformation. Without the constant downward pull of gravity, the fluids that normally pool in the legs and lower torso rush upward toward the chest and head. This fluid shift, occurring within minutes of weightlessness, causes the face to puff up, the legs to thin, and the sinuses to congest, a condition astronauts often describe as a perpetual head cold. But this visible change is merely the surface manifestation of a profound physiological upheaval. The cardiovascular system, no longer fighting to pump blood uphill against gravity, begins to slacken. The heart actually changes shape, becoming more spherical and losing muscle mass over time, a degradation that can lead to orthostatic intolerance, where returning to Earth's gravity causes immediate fainting as the heart struggles to relearn how to pump vertically. Deep inside the skeletal structure, a more silent and dangerous erosion takes place. In the absence of mechanical loading, the body concludes that its structural supports are no longer necessary. Osteoclasts, the cells responsible for breaking down bone tissue, go into overdrive, while osteoblasts, the bone builders, slow their work. The result is a loss of bone density occurring at a rate of 1 to 2% per month, a speed that mimics aggressive osteoporosis, but occurs in healthy individuals. This liberated calcium floods the bloodstream and filters through the kidneys, creating a high risk of renal stones, a potentially mission-ending medical emergency in a remote environment. Muscle atrophy mirrors this skeletal decay, particularly in the anti-gravity muscles of the back, calves, and thighs. Without rigorous intervention, an astronaut could lose up to 20% of their muscle mass in just a few weeks, leaving them too weak to perform emergency egress procedures upon landing or to function effectively during extravehicular activities. While the mechanical degradation of the body is manageable with effort, the invisible assault of space radiation presents a threat that is far more difficult to mitigate. Outside the protective embrace of Earth's magnetosphere, the human body is bombarded by galactic cosmic rays and solar particle events. These high-energy particles tear through the hull of the spacecraft and the flesh of the crew, shattering DNA strands and increasing the lifetime risk of cancer. During the Apollo missions, astronauts reported seeing flashes of light even with their eyes closed, a phenomenon caused by cosmic rays passing physically through their retinas. Current data suggests that on a long-duration mission to Mars, the cumulative radiation dose could exceed the career limits currently set by space agencies, necessitating new shielding strategies or pharmaceutical radioprotectors. The brain itself is not immune. Animal studies indicate that heavy ion radiation can damage neural networks, potentially affecting cognitive function and memory, a risk that adds a layer of neurological uncertainty to deep space travel. The psychological toll of leaving Earth is as significant as the physical one. The phenomenon known as the break-off effect, a feeling of detachment and spiritual isolation, has been reported since the early days of high-altitude balloon flights and continues to affect those in orbit. Confined to a tin can surrounded by an infinite void, astronauts face a unique set of stressors including isolation, confinement, and the total lack of privacy. Space psychologists have identified the third quarter of a mission as the most dangerous period, where morale dips and interpersonal conflicts are most likely to flare. The view of Earth, the blue marble, often provides a profound psychological anchor, a cognitive shift known as the overview effect that fosters a sense of global unity. However, as missions venture further out, Earth will shrink to a mere point of light, removing that visual connection and potentially triggering deep existential distress. To combat these physiological and psychological erosions, life on the International Space Station has become a regimented battle for health. Countermeasures are woven into the daily existence of every crew member. They spend approximately 2 hours every day strapped to specialized treadmills and resistive exercise devices, generating the mechanical loads necessary to trick their bones and muscles into maintaining density. Dietary supplements, including vitamin D and bisphosphonates, are used to support skeletal health, while rigorous fluid tracking helps mitigate kidney stone risks. To handle the vestibular disruption, the sensory conflict between the inner ear and the eyes that causes nausea and disorientation known as space adaptation syndrome. As we look toward longer missions, these countermeasures must evolve, becoming more efficient and less resource-intensive to ensure the human machine survives the journey. The chemical rockets that have carried humanity to the moon and built the space station are engineering marvels, yet they remain shackled by the tyranny of the rocket equation. To go further and faster, we must move beyond the controlled explosions of liquid oxygen and kerosene. The immediate future of deep space propulsion lies in nuclear thermal systems. By passing a propellant, generally liquid hydrogen, through a nuclear reactor core, the fluid is superheated and expanded through a nozzle. This process yields a specific impulse, a measure of fuel efficiency that is roughly double that of the best chemical engines. NASA and other agencies are actively revitalizing these designs, which were first tested in the 1960s, to create a transport system capable of delivering crew to Mars in months, rather than nearly a year, drastically reducing radiation exposure and supply requirements. While nuclear thermal propulsion offers high thrust, electric propulsion offers unparalleled efficiency for cargo and long-term station keeping. Ion engines and Hall-effect thrusters use electricity to ionize a gas, usually xenon, and accelerate it out of the back of the engine at tremendous speeds. The thrust produced is low, often compared to the weight of a piece of paper on your hand, but it can be sustained for months or years. This continuous acceleration allows spacecraft to build up incredible velocities over time. Current developments focus on scaling these systems up, using high-power solar arrays or onboard nuclear reactors to drive massive plasma engines that could haul heavy infrastructure to the outer planets, serving as the tugboats of a future solar system economy. Looking further toward the horizon, theoretical physics offers glimpses of propulsion systems that could unlock the stars themselves. Fusion propulsion, which seeks to replicate the power of the sun within a magnetic bottle, promises specific impulses orders of magnitude higher than chemical rockets. If the engineering challenges of sustaining a fusion reaction can be solved, a fusion drive could carry humans to the moons of Jupiter in weeks. Even more exotic is the concept of antimatter propulsion. The collision of matter and antimatter releases energy with 100% efficiency, the ultimate density of power. While currently we can only produce antimatter in nanogram quantities at immense cost, the theoretical designs for antimatter-catalyzed fusion engines suggest a future where interstellar travel becomes a matter of decades rather than millennia. For missions that require no fuel at all, engineers are turning to the momentum of light itself. Solar sails utilize the pressure of photons striking a large reflective surface to generate thrust. Like a ship catching the wind, a solar sail requires no onboard propellant, allowing it to accelerate indefinitely as long as it remains within sight of the sun or a powerful laser source. Breakthroughs in materials science have led to ultra-lightweight, highly reflective films that make these sails viable for reconnaissance missions to near-Earth asteroids or as listening posts in the outer solar system. Laser propulsion takes this concept a step further, proposing to leave the energy source on Earth or in orbit. By firing a massive laser at a spacecraft equipped with a sail or a heat exchanger, we can drive the vessel to high speeds without forcing it to carry the heavy burden of fuel, breaking the rocket equation entirely. Even within the realm of conventional rocketry, innovation has not stalled. The shift toward methane-based fuels represents a critical evolution. Methane burns cleaner than kerosene, reducing soot buildup in reusable engines, and crucially, it can be synthesized from the Martian atmosphere using the Sabatier reaction. This capability for in-situ resource utilization means that future explorers will not need to bring their return fuel with them. They will manufacture it on the red planet. Combined with the rapid iteration of full-flow staged combustion cycles, which squeeze every ounce of energy from the propellant, the traditional rocket is becoming a reusable workhorse, a reliable shuttle to orbit that serves as the first link in a chain of exotic technologies stretching out to the planets. Survival in the vacuum of space relies on a delicate closed-loop mechanical ecosystem where every molecule matters. The Environmental Control and Life Support System, or ECLSS, is the mechanical heart of any long-duration habitat. On the International Space Station, this system has achieved a water recovery rate of over 90%, capturing humidity from the air and recycling urine into potable water. For a journey to Mars, this efficiency must approach 98% or higher. The psychological hurdle of drinking recycled urine is overcome by the reality that the water produced is purer than most municipal supplies on Earth. Air revitalization is equally critical, using electrolysis to split water into breathable oxygen and venting hydrogen, or reacting it with waste carbon dioxide to reclaim water. The challenge lies in reliability. These systems cannot fail when the nearest replacement part is millions of miles away, necessitating self-healing materials and 3D printable components. The absence of gravity remains one of the most persistent threats to long-term habitation, leading engineers to revisit the concept of artificial gravity. While science fiction depicts massive rotating wheels, the engineering reality is a complex trade-off between size, rotation rate, and the Coriolis effect. A small centrifuge spinning rapidly creates gravity, but the difference in force between a crew member's head and feet can cause severe nausea and disorientation. Large, slowly rotating habitats avoid this, but require immense structural integrity and mass. Current proposals explore tether systems, where a habitat module and a spent rocket stage or counterweight are connected by a mile-long cable and spun around a center of gravity, creating a comfortable 1G environment that would negate the bone and muscle loss associated with microgravity, effectively solving the physiological degradation problem at the source. Shielding the crew from the lethal bath of space radiation requires materials that are both lightweight and hydrogen-rich, as hydrogen is effective at scattering cosmic rays. Water is an excellent shield, leading to habitat designs where the water storage tanks create a protective jacket around the sleeping quarters. Polyethylene and newly developed hydrogenated boron nitride nanotubes offer structural strength combined with radiation protection. Beyond passive shielding, researchers are investigating active shielding, generating a magnetic bubble around the spacecraft that mimics Earth's magnetosphere to deflect charged particles. While currently requiring prohibitive amounts of power, advances in superconducting magnets could make these force fields a reality, providing a safe haven for astronauts during solar storms. A true spacefaring civilization cannot rely on packed lunches. It must grow its own food. The veggie experiments on the ISS have proven that lettuce and other greens can grow in microgravity, provided they have the right light spectrum and a medium to deliver water to the roots. Future habitats will likely incorporate aeroponics and hydroponics on a massive scale, turning the walls of the spacecraft into vertical gardens. This bioregenerative approach serves a dual purpose. The plants provide calories and psychological comfort while also consuming carbon dioxide and producing fresh oxygen. For protein, cellular agriculture and insect farming offer high-density nutrition with minimal waste, though the cultural acceptance of such diets remains a hurdle that space agencies are actively studying. Underlying all these systems is the absolute necessity of redundancy and emergency management. In deep space, there is no abort mode that returns the crew to Earth in hours. Fire suppression systems must work without using materials that contaminate the breathable air. Hull breaches must be detected and sealed instantly, potentially by smart materials that react to pressure drops by expanding to plug the hole. The concept of the safe haven, a heavily shielded, independently powered section of the ship stocked with emergency supplies, is central to habitat design. This bunker mentality ensures that even if the primary life support fails or a solar flare overwhelms the main shielding, the crew has a fighting chance to survive until repairs can be made or the storm passes. To cross the vast gulfs between the outer planets, or to venture toward nearby stars, the human clock must be slowed. The distances involved in deep space travel are so great that a standard human lifespan becomes a limiting factor. Scientists are actively investigating therapeutic hypothermia and torpor, states of suspended animation that could reduce a crew member's metabolic rate by 50 to 70%. By cooling the body and administering specific pharmaceutical agents, astronauts could sleep for weeks or months at a time. This would not only reduce the psychological strain of boredom and confinement, but also drastically cut the consumables required for the mission. A crew in torpor eats less, breathes less, and requires less living space, allowing for smaller, faster ships. The challenge lies in the safety of the induction and wake-up processes, ensuring that the brain and organs suffer no damage from the prolonged metabolic suppression. Medical autonomy is the cornerstone of deep space survival. As the communication delay with Earth stretches from minutes to hours, the crew cannot rely on mission control for medical advice during an emergency. The spacecraft must effectively become a hospital, equipped with automated diagnostic tools and robotic surgical systems. Artificial intelligence will play a critical role here, acting as the onboard physician capable of diagnosing illnesses from biometric data and guiding the crew through complex procedures. Advances in 3D bioprinting may allow for the on-demand fabrication of skin grafts for burns or even simple organ tissues, while a pharmacy on a chip could synthesize specific medications from raw chemical precursors, solving the problem of drug expiration dates on multi-year missions. The integration of artificial intelligence extends beyond medicine to the very operation of the vessel. A ship traveling to the Kuiper Belt or beyond must be sentient in its own right. It must be able to detect a system failure, isolate the cause, and reroute power or data without human intervention. This autonomous operation capability is vital when the crew is incapacitated or in torpor. The AI serves as the nervous system of the ship, constantly monitoring hull integrity, life support efficiency, and trajectory. However, this reliance on AI necessitates robust safeguards against software errors and hallucinations, requiring a tiered command structure where human judgment remains the final arbiter for critical decisions, ensuring the tool remains a servant rather than a master. Communication across the solar system faces the immutable barrier of the speed of light. To maximize the data return from deep space, we are moving from radio waves to optical communication. Laser communication systems can transmit data at rates 10 to 100 times faster than current radio frequency systems, allowing for high-definition video and massive scientific data dumps. This precision requires incredible pointing accuracy, akin to hitting a coin from a mile away, but the technology has already been demonstrated. On the theoretical fringe, quantum entanglement offers the tantalizing, though currently scientifically disputed, possibility of instantaneous communication. While current physics suggests information cannot travel faster than light, research into quantum key distribution ensures that whatever communication does occur is perfectly secure, immune to interception or tampering. The spacecraft itself must be designed for an operational life measured in decades. The concept of maintenance-free is a myth. Instead, the design philosophy is repair-friendly. Components must be modular, standardized, and accessible. If a pump fails, it should be replaceable with a generic spare that can also serve as a fan motor or a drill. This universality reduces the inventory of spare parts. Furthermore, the hull must be self-healing. Materials embedded with vascular networks containing liquid healing agents can automatically seal microcracks caused by fatigue or micrometeoroid impacts. The ship becomes a living organism, regenerating its skin and regulating its internal environment, carrying its fragile human cargo through the silence of the void with a resilience that mirrors biological life. The transition from visitation to habitation requires a fundamental shift in how we view space architecture. We are moving away from the camping trip model of the Apollo era towards self-sustaining colonies. Whether these are O'Neill cylinders, massive rotating habitats in free space, or domed cities on the lunar surface, the requirement is the same: the environment must be manufactured. Planetary bases will likely utilize lava tubes, natural caverns formed by ancient volcanic activity, to provide ready-made protection against radiation and temperature extremes. By sealing these subterranean cathedrals and pressurizing them, we can create vast habitable volumes that dwarf anything we could build on the surface. These cities will be multi-generational, requiring parks, recreational facilities, and private spaces that mimic the chaotic comfort of Earth, vital for the mental health of a permanent population. The economic engine of a spacefaring civilization is in situ resource utilization. It is prohibitively expensive to launch everything from Earth's deep gravity well. Therefore, the moon and asteroids become the quarries and hardware stores of the future. Regolith, the dust covering the moon, can be sintered by microwaves into bricks for construction or processed to extract oxygen and silicon. Metallic asteroids offer practically infinite supplies of iron, nickel, and platinum group metals. Automated mining swarms will harvest these materials, feeding orbital refineries that 3D print truss structures and pressure vessels in the vacuum. This decoupling of construction from Earth launch constraints allows for structures of immense scale, turning space from a destination into a place of industry and production. As communities form off-world, the social and governmental structures of Earth will be tested and likely transformed. A colony on Mars cannot be effectively governed by a bureaucracy in Washington or Brussels when the communication lag is 20 minutes and the reality of survival is visceral. Sociologists predict the emergence of technocratic collectives, where expertise and contribution to the life support systems determine social standing. However, the harsh environment necessitates strict discipline, potentially leading to authoritarian structures if not carefully balanced with democratic principles. The constitution of Mars will need to address the right to oxygen, the allocation of procreation rights in a limited gene pool, and the resolution of conflicts where exile is a death sentence. The economy of space will evolve from government-funded exploration to a robust commercial ecosystem. Initially driven by tourism and satellite servicing, the long-term economy will likely pivot to energy and information. Space-based solar power beaming clean energy down to Earth via microwaves offers a limitless power source that could justify the massive infrastructure costs. Additionally, the unique environment of microgravity allows for the manufacturing of fiber optic cables with zero defects and perfect protein crystals for pharmaceutical research, products that are high value enough to justify the transport costs. This trade between Earth and the colonies creates a symbiotic relationship, where the colonies provide exotic goods and energy in exchange for the biological complexity and cultural output of the home world. Education in a space settlement will be radically different from Earth-based schooling. Children born in a colony will be apprentices to survival from a young age. The curriculum will be intensely practical, focusing on engineering, botany, and systems thinking. Every citizen must be a technician capable of repairing an air scrubber or sealing a breach. However, to prevent cultural stagnation, the arts and humanities must be preserved and adapted. These future generations will develop their own dialect, their own folklore, and their own artistic expression born from the stark beauty of their environment. They will be the first true extraterrestrials, humans whose concept of home is a rotating cylinder or a red desert, separated from Earth not just by distance, but by a fundamental divergence in culture and experience. The trajectory of the next 50 years points toward a bifurcation of human history, a split between those who remain terrestrial and those who become celestial. The timeline suggests that within the next decade, we will see the permanent return of humans to the moon, establishing the Artemis base camp as a proving ground. By the late 2030s, the first crewed missions to Mars will likely launch, a venture that will be as much a test of political will as technological capability. The 2040s and 2050s will see the expansion of orbital industry, with private space stations replacing the ISS and the first commercial asteroid mining operations, bringing platinum and water back to the cislunar economy. This era will be defined by the transition from exploration to exploitation as the business case for space finally closes. This expansion is no longer the sole province of superpowers. The privatization of space travel has introduced a dynamism and risk tolerance that government agencies cannot match. We are witnessing a race not between nations but between philosophies. Open architectures versus proprietary systems, scientific cooperation versus commercial dominance. International treaties like the Outer Space Treaty of 1967 are already straining under the pressure of these new realities. The question of who owns the ice in a lunar crater, or who has liability for a defunct satellite crashing into a habitat, will drive a new era of space law. Cooperation will likely be driven by necessity. The hostility of the environment makes mutual aid a survival imperative, potentially fostering a diplomatic unity in space that remains elusive on Earth. As humans spend generations in low gravity, we must confront the reality of evolutionary divergence. A child born on Mars, under 38% of Earth's gravity, will develop a physiology distinct from their Terran cousins. They may be taller, with lighter bones and a cardiovascular system tuned to lower resistance. Bringing a third-generation Martian back to Earth might be physically impossible, the high gravity crushing their adapted frame. This biological separation raises profound ethical questions. Are we creating a new species of human? Genetic engineering, likely necessary to bolster radiation resistance, will accelerate this drift. We may eventually see the rise of Homo sapiens a branch of humanity adapted for the void, leading to a speciation event driven by technology and geography. The ethical landscape of this expansion is treacherous. We must decide if we have the right to contaminate other worlds with our microbes, potentially wiping out indigenous microbial life before we even discover it. The concept of planetary protection is clashing with the urge to colonize. Furthermore, the immense cost of space settlement raises issues of equity. If space becomes a lifeboat for humanity, who gets a seat? There is a risk that space becomes the exclusive domain of the wealthy and the genetically selected, leaving a resource-depleted Earth behind. Policy decisions made today regarding resource ownership and launch access will determine whether space becomes a commons for all humanity or a high ground for a new elite. Ultimately, the drive to become a multiplanetary species is an insurance policy for consciousness. Earth is fragile, subject to asteroid impacts, supervolcanoes, and anthropogenic self-destruction. Spreading the light of human intelligence to other worlds ensures that the story of humanity does not end with a single catastrophe. It forces us to grow up, to manage closed ecosystems, to live peacefully in confined spaces, and to look outward with a sense of shared destiny. The road ahead is dangerous, expensive, and uncertain, but it offers the only path to a future where the human experience is not bound by the expiration date of a single planet. We are stepping off the ledge, not because it is easy, but because the horizon demands it. The dream of traversing the cosmos is immediately confronted by the rigid, unyielding laws of physics, the most formidable of which is the speed of light. In the vacuum of space, light travels at approximately 186,000 miles per second, a cosmic speed limit enforcement that Albert Einstein codified in his theory of special relativity. This is not merely an engineering hurdle or a limitation of current technology that might be bypassed with better engines. It is a fundamental property of the universe's causal structure. To accelerate an object with mass to the speed of light would require an infinite amount of energy, a physical impossibility. As a spacecraft approaches this universal barrier, its mass effectively increases, requiring exponentially more energy to gain even a fraction more speed, creating a curve of diminishing returns that walls us off from the rest of the galaxy. Even if we could achieve a significant percentage of light speed, the distances involved render the term travel woefully inadequate. The nearest star system, Alpha Centauri, sits over 4 light-years away. At the speeds achieved by the Voyager probes, which are among the fastest objects ever built by human hands, the journey would take nearly 80,000 years. This timescale is longer than the entirety of recorded human history. To make such a journey within a human lifetime, we would need to travel at relativistic speeds, perhaps 10 or 20% of the speed of light. Achieving this requires propulsion systems that exist currently only on chalkboards or in the fevered dreams of futurists. Chemical rockets, the workhorses that lifted us to the moon and built the International Space Station, are pitifully insufficient for interstellar distances. The energy density of chemical fuel is simply too low to carry enough fuel to accelerate a ship to relativistic speeds. The ship would need to be the size of a planet, most of which would be fuel used just to lift the other fuel. This leads us to the Tsiolkovsky rocket equation, a mathematical tyrant that dictates the cruel relationship between fuel mass, payload mass, and velocity. The equation reveals that for every ounce of speed gained, the mass of the propellant required grows exponentially. To break this tyranny, we must abandon chemical fire and turn to the primal forces of the atom. Nuclear pulse propulsion, a concept explored in the mid-20th century under Project Orion, offered a brutal but effective solution. The design called for a massive spacecraft equipped with a thick pusher plate, behind which nuclear bombs would be ejected and detonated in rapid succession. The plasma from the explosions would slam into the plate, driving the ship forward with immense force. While theoretically capable of reaching significant fractions of light speed, the concept was shelved due to the Nuclear Test Ban Treaty and the terrifying prospect of launching a vessel loaded with thousands of nuclear warheads. However, the physics of nuclear pulse propulsion remains one of the few viable methods for moving large masses across interstellar distances within a reasonable timeframe. It represents a brute force conquest of the void, riding the shockwaves of our most destructive creations to reach the stars. A more refined cousin of this concept is nuclear fusion propulsion. Unlike the uncontrolled fission of Orion, a fusion drive would sustain a controlled reaction, similar to the processes powering the Sun, expelling high-energy particles to generate thrust. The challenge lies in containment and energy balance. We have yet to build a fusion reactor on Earth that produces significantly more energy than it consumes, let alone one compact and durable enough to serve as an engine for a starship. The fuel for such a drive, likely isotopes of hydrogen like deuterium and helium-3, would need to be harvested from gas giants or the lunar surface, adding an entire industrial infrastructure prerequisite to the launch itself. If fusion is the engine of the stars, antimatter is the engine of the gods. When matter meets antimatter, they annihilate completely, converting their entire mass into pure energy in accordance with Einstein's famous equation. This reaction is orders of magnitude more energetic than nuclear fusion. A spacecraft powered by antimatter could theoretically reach a significant percentage of the speed of light with a relatively small amount of fuel. The efficiency is absolute. However, the production and storage of antimatter present hurdles that border on the insurmountable. Currently, we produce antimatter in particle accelerators atom by atom at a cost of trillions of dollars per gram. To produce enough to fuel a starship would require global energy output dedicated solely to this task for centuries. Furthermore, containing this volatile substance requires magnetic fields of perfect reliability. If the containment fails for even a microsecond, the fuel touches the tank walls and the ship vanishes in a burst of gamma radiation brighter than 1,000 suns. Despite these dangers, antimatter remains the gold standard for theoretical propulsion. It offers the highest specific impulse of any known reaction. Yet, even with such power, the universe imposes another penalty: time dilation. As a ship accelerates closer to the speed of light, time on board slows down relative to the rest of the universe. For the astronauts, a journey to the center of the galaxy might take only a few decades of ship time. They would age normally, live their lives, and perhaps reach their destination before dying of old age. But upon their arrival, or their return to Earth, they would find that tens of thousands of years had passed for the people they left behind. Civilizations would have risen and fallen, the very languages they spoke would be dead. Interstellar travel at relativistic speeds is effectively a one-way trip into the future. The traveler is severed from their timeline, becoming a ghost in a future that has forgotten them. This twin paradox ensures that while humans might visit the stars, they can never truly share the experience with the world that sent them. While the engineering challenges of propulsion are daunting, the biological limitations of the human organism are perhaps even more severe. We evolved within the protective embrace of Earth's atmosphere and magnetosphere, shielded from the harsh realities of the cosmos. Deep space is a bath of high-energy radiation, primarily galactic cosmic rays. These are protons and atomic nuclei moving at nearly the speed of light, stripped of their electrons and originating from supernovae explosions light-years away. Unlike the solar wind, which can be blocked by shielding, GCRs are like subatomic bullets that tear through metal and flesh alike. When they strike human DNA, they shatter the double helix, causing mutations, cancer, and acute radiation sickness. Shielding a ship against GCRs would require meters of lead or water, adding massive weight that exacerbates the propulsion problem. Beyond radiation, the absence of gravity wreaks havoc on human physiology. In microgravity, the body begins to discard what it deems unnecessary. Bones lose density at an alarming rate, becoming brittle and prone to fracture, a condition akin to accelerated osteoporosis, muscles atrophy, and the heart, no longer fighting gravity to pump blood upward, shrinks and weakens. Fluids shift toward the head, increasing intracranial pressure and pressing against the optic nerve, leading to permanent vision impairment, a syndrome already observed in astronauts on long-duration station missions. If we are to travel for years or decades, we must either generate artificial gravity through the rotation of massive centrifugal habitats, or genetically engineer the crew to withstand an environment for which biology has no precedent. The psychological toll of interstellar travel is equally devastating. The phenomenon known as the break-off effect, experienced by high-altitude pilots and astronauts, describes a feeling of detachment and anxiety when the Earth is reduced to a visual abstraction. On a journey to another star, Earth would eventually disappear from the naked eye entirely, reducing the homeworld to just another speck in the star field. This total isolation, combined with confinement in a metal canister with the same small group of people for decades, is a recipe for psychological breakdown. The social dynamics of a crew trapped in a high-stress, low-stimulus environment could devolve into tribalism or madness. To mitigate this, mission planners have proposed putting crews into varying states of torpor or hibernation, lowering metabolic rates to sleep through the long dark. While common in science fiction, human hibernation is medically unproven. We do not possess the physiological mechanisms of bears or squirrels. Inducing a low metabolic state without causing brain damage or organ failure remains beyond our current medical capability. If we cannot travel fast enough to reach the stars within a single human lifetime, and if we cannot sleep through the journey, the alternative is the generation ship. This is a massive, self-sustaining ark designed to travel at sublight speeds for centuries or millennia. The crew that launches the ship will not be the crew that arrives. They are merely the ancestors, destined to live and die in the void, so that their great-great-grandchildren might walk on a new world. This concept shifts the challenge from propulsion to sociology and ecology. A generation ship must be a perfect closed-loop ecosystem. Every gram of water, every breath of air, and every nutrient must be recycled with 100% efficiency. Entropy is the enemy here. Any small loss of resources over a 1,000-year voyage spells extinction. The social structure of a generation ship presents a profound ethical dilemma. The intermediate generations are born into a prison they did not choose, conscripted by their ancestors into a mission they may not believe in. They are destined to be caretakers of a hull, maintenance workers for a dream they will never see fulfilled. How does a society maintain a singular purpose over centuries? Cultures drift, languages evolve, historical records are reinterpreted or lost. A ship that leaves Earth with a mission of exploration might arrive at its destination populated by a distinct culture that has forgotten why they are traveling or has developed a religion based on the mythology of the launch. The risk of mutiny, civil war, or simply a loss of technical competence is high. If the knowledge of how to repair the propulsion system is lost or becomes ritualized rather than understood, the ship becomes a drifting tomb. To ensure the genetic viability of the population, a generation ship would need a starting crew of thousands, or a bank of frozen embryos and artificial wombs to introduce genetic diversity. The sheer scale of such a vessel, essentially a moving city, requires construction in orbit and the mining of asteroids for materials. It represents a civilization-level commitment of resources. The moral weight of condemning unborn generations to a life inside a machine, surrounded by the lethal vacuum, is a heavy burden. It forces us to ask whether the survival of the species is worth the sacrifice of the individual liberty of those traveling the void. Given the immense difficulties of moving mass through space, theoretical physics offers a tantalizing alternative: moving space itself. The Alcubierre drive, proposed by physicist Miguel Alcubierre, is a theoretical solution to the Einstein field equations that allows for faster-than-light travel without locally breaking the light speed limit. The concept involves creating a bubble of space-time around a ship. Space in front of the ship is contracted, pulling the destination closer, while space behind the ship is expanded, pushing the departure point away. The ship itself sits in a flat region of space-time inside the bubble, feeling no acceleration and experiencing no time dilation. To the occupants, the journey would take days or weeks, and they would arrive in sync with the universe's clock. However, the Alcubierre drive requires a form of energy that may not exist, negative energy. To warp spacetime in the required geometry, the drive needs a ring of exotic matter with negative mass. While quantum mechanics allows for the existence of negative energy densities in specific circumstances, such as the Casimir effect, scaling this up to the magnitude required for a starship is currently impossible. Early calculations suggested the drive would require more energy than exists in the observable universe. Refined models have brought this down to the mass-energy equivalent of Jupiter, which is still an astronomical quantity. Furthermore, the physics of the drive creates causality problems. If faster-than-light travel is possible, it implies the ability to send information back in time, violating the basic principles of cause and effect that hold reality together. Another theoretical shortcut is the Einstein-Rosen bridge, or wormhole. These are tunnels through the fabric of spacetime that connect two distant points. If one could be stabilized and traversed, a journey of 1,000 light-years could be reduced to a single step. Yet, wormholes are inherently unstable. They tend to collapse the instant anything, even a single photon, attempts to enter them. Keeping a wormhole open would, like the warp drive, require negative energy or exotic matter to act as a scaffold against the crushing force of gravity. Additionally, we have no idea how to create a wormhole or how to target the exit. A naturally occurring wormhole might lead to the center of a star, a black hole, or deep intergalactic space. Relying on them is less like building a road and more like jumping into a hurricane, hoping to land in a specific backyard on the other side of the world. The final and perhaps most sobering realization of space travel is the limit imposed by the expansion of the universe itself. We live in a universe that is not static. It is expanding, and that expansion is accelerating due to dark energy. The galaxies we see in the night sky are moving away from us. There is a cosmic horizon, a distance beyond which objects are receding faster than the speed of light. Light emitted by galaxies beyond this horizon will never reach us, and we can never reach them, no matter how fast we travel or how advanced our technology becomes. They are causally disconnected from us forever. This means that the reachable universe is shrinking every second. As time goes on, more and more galaxies will cross this horizon and vanish from our view. Eventually, billions of years in the future, the only galaxies visible to us will be those in our own local group, the Milky Way, Andromeda, and a few dozen smaller satellite galaxies. These are bound to us by gravity, but everything else will have accelerated away into the darkness. Any civilization that arises in the distant future will look up at a sky that is largely empty, unaware of the vast, teeming cosmos that once was. This imposes a hard limit on human expansion. We are not destined to inherit the entire universe. We are confined to a local pocket of it. The dream of a galactic empire spanning the entirety of creation is physically impossible. We are prisoners of the local group, bound by the expansion rate of the cosmos. Faced with the frailty of the human body and the vastness of the void, many scientists argue that the future of space travel is not biological but technological. The era of sending meat sacks in metal cans may be a brief, primitive phase. The true travelers of the stars will be von Neumann probes, self-replicating machines capable of mining resources, building copies of themselves, and spreading exponentially throughout the galaxy. A single probe launched today could theoretically colonize the entire Milky Way in a few million years, a blink of an eye in cosmic time. These probes would not suffer from radiation sickness, loneliness, or old age. They could power down for millennia, drifting through the interstellar voids, and wake up only upon arrival at a new system. This line of thinking leads to the concept of substrate-independent minds. If human consciousness can be mapped and uploaded to a durable hardware substrate, the distinction between passenger and ship vanishes. A digital consciousness could travel at the speed of light as a stream of data, beamed by laser to a receiver station in another system, or reside within a hardened probe. In this form, a human mind could slow down its perception of time, making a 1,000-year journey feel like a momentary pause. This transcends the biological limits entirely. We would no longer need life support, gravity, or food. We would become creatures of energy and silicon. adapted to the hostile environment of space rather than fighting against it. This post-biological future suggests that our current obsession with rockets and habitats is merely the embryonic stage of a species preparing to shed its physical shell. The ultimate traveler is not the astronaut, but the information that defines the astronaut. By decoupling intelligence from biology, we remove the expiration date on the traveler. We could explore the universe not as fragile tourists, but as immortal entities woven into the fabric of the technology that carries us. This shift changes the definition of human travel. Is it still humanity if the heart no longer beats? Is the colonization of the galaxy by our machines a victory for us, or merely the succession of a new synthetic species? The immense difficulty of space travel brings us face to face with the Fermi paradox. If interstellar travel is possible, even at sublight speeds, the galaxy should be teeming with civilizations. Given billions of years, a species should have spread everywhere. Yet, we see silence. We see no Dyson spheres, no stellar engines, no loud radio chatter. This silence suggests the existence of a great filter, a probability barrier that prevents life from reaching the stage of interstellar colonization. It is possible that the hurdles we face, the distance, the radiation, the energy requirements, are that filter. Perhaps civilizations invariably destroy themselves with the very technologies required to leave their homeworlds, or perhaps the economic and social cost of space travel is simply too high for any rational species to sustain. It is also possible that we are the first. The universe is young in terms of star formation. We may be the early risers in a cosmos that is just waking up. If this is true, the responsibility weighing on us is even heavier. We are not just exploring for ourselves, we are carrying the only torch of consciousness in a vast, dark room. If we extinguish ourselves or fail to leave Earth, the universe may remain silent for billions of years more. The drive to travel through space is therefore not just a quest for resources or territory. It is a battle against the silence, a struggle to ensure that the universe observes itself. Returning to the realm of the possible, one of the most promising technologies for near-future interstellar travel is the light sail. Instead of carrying heavy fuel, a light sail relies on the momentum of photons. A massive laser array built on Earth or the Moon would beam a concentrated stream of light at a highly reflective sail attached to a small probe. This concept, exemplified by the Breakthrough Starshot initiative, aims to accelerate gram-scale probes to 20% of the speed of light. These nanocraft could reach Alpha Centauri in 20 years. They would be the scouts, the first human-made objects to capture images of another Earth-like world. The physics of light sails scales elegantly. While a gram-scale probe is the starting point, immense sails spanning kilometers could theoretically push crewed vessels. The engineering challenge shifts from onboard propulsion to the construction of massive laser infrastructure in the solar system. This effectively leaves the engine at home. The ship becomes a passive rider on a beam of light. However, stopping is a problem. Without a laser array at the destination to slow the ship down, it would fly past the target system at relativistic speeds, gathering data for only a few hours before hurtling into the deep void forever. To stop, a ship would need to deploy a magnetic sail to drag against the interstellar medium or detach a section of the sail to reflect light from the destination star, a maneuver requiring precise automated navigation. The space between stars is not truly empty. It is filled with the interstellar medium ISM, a tenuous soup of gas, dust, and cosmic rays. At relativistic speeds, this medium becomes a formidable barrier. A single grain of sand hitting a ship traveling at 20% of the speed of light carries the kinetic energy of a nuclear bomb. The hull of an interstellar vessel must be armored against this constant bombardment. Concepts for shielding include thick layers of ice, Whipple shields, or even active magnetic fields that ionize and deflect incoming particles. The ISM also presents a drag factor. Just as a car pushes against air, the starship pushes against the thin gas of the galaxy. Over light years, this drag can significantly sap the momentum of a vessel, requiring constant thrust to maintain velocity. However, this medium also offers an opportunity. The Bussard ramjet is a theoretical engine design that uses a massive magnetic funnel. thousands of kilometers wide, to scoop up the interstellar hydrogen and feed it into a fusion reactor. In theory, this provides a ship with infinite fuel, allowing it to accelerate indefinitely. In practice, the drag created by the funnel might exceed the thrust generated by the engine, a braking effect that renders the design useless unless we can find a way to catalyze fusion more efficiently than currently thought possible. We cannot discuss the distance humans can travel without addressing the cost. The energy required to send a single human to Mars is immense. The energy to send a colony to a nearby star is comparable to the current total annual energy consumption of the human race. Building the infrastructure for interstellar travel, the orbital shipyards, the lunar mines, the laser arrays, requires a global economy that is post-scarcity or unified in a way that currently seems utopian. The venture capital model that fuels modern spaceflight cannot apply to a mission that yields no return on investment for centuries. Who pays for a ship that will not arrive for 500 years? What government funds a project that will only benefit the distant descendants of its taxpayers? Interstellar travel requires a fundamental shift in human temporal perception. We must move from quarterly profit cycles to millennial thinking. It requires a species-wide altruism, a willingness to plant trees under whose shade we will never sit. This economic and cultural barrier is perhaps as rigid as the speed of light. Without a unified planetary civilization capable of long-term planning, the stars will remain distant lights, admired but never touched. Let us look closer at the suspension of life. If we can master the biology of hibernation, the galaxy opens up. The sleeper ship avoids the sociological nightmare of the generation ship. The crew that leaves is the crew that arrives. They retain their skills, their memories, and their dedication to the mission. The technology requires mastering the regulation of adenosine in the brain, the prevention of cellular damage from freezing, and the automated medical systems to revive the crew. Current research into therapeutic hypothermia gives us clues. We know we can cool a body to stop the heart for surgery, but keeping a body in stasis for decades involves halting entropy in the cells. If successful, a sleeper ship could travel at slower, more achievable speeds. A voyage of 1,000 years becomes instantaneous for the traveler. They would close their eyes in the orbit of Earth and open them in the orbit of Proxima b. The tragedy, of course, is the dislocation. They would wake up to a universe where everyone they ever knew has been dead for a millennium. They would be archaeological artifacts, living fossils of a bygone era, tasked with building a new world. Every spaceship is a battle against the second law of thermodynamics. Heat is the ultimate enemy. In the vacuum of space, getting rid of waste heat is incredibly difficult, because there is no air to conduct it away. It must be radiated as infrared light. A ship generating the power of a nuclear reactor for propulsion must have massive radiators, glowing red hot, to prevent the crew from being cooked alive. These radiators are vulnerable points, fragile wings that, if damaged, doom the ship. Furthermore, a closed ecosystem must manage the heat generated by the bodies of the crew and the electronics. The efficiency of recycling systems must be absolute. If a water recycling system is 99.9% efficient, the 0.1% loss will eventually kill everyone on a long enough timeline. We need systems that are 100% efficient, essentially violating the natural tendency of things to degrade. This requires energy input to reverse entropy locally, further increasing the fuel requirements. The mathematics of survival in deep space is a razor's edge equation, where the margins for error are non-existent. Ultimately, the limit of how far we can travel may not be defined by the rocket or the reactor, but by the mind. The human brain is adapted for the savannah, for small groups, for the horizon of a planet. We are not adapted for the infinite void. The overview effect creates awe, but the exodus effect, the permanent loss of Earth, may create a trauma we cannot predict. Can a human mind remain sane when removed from the biological context that created it? We may find that to travel the stars, we must change what it means to be human. We may need to edit our genomes to remove the need for social validation, to enhance our tolerance for isolation, to adapt our circadian rhythms to the silence of space. The travelers who reach the edge of the galaxy may not be Homo sapiens as we know them. They will be a divergent species, forged by the requirements of the void. In this sense, humans can travel as far as we are willing to let go of our humanity. The distance is limited only by our willingness to transform. Our immediate cosmic neighborhood, the local bubble, is a cavity in the interstellar medium roughly 300 light-years across. Within this bubble lie thousands of stars. This is the playground for the next 10,000 years of human history. Exploring this region alone is a task of monumental scale. Beyond it lies the Gould Belt, a ring of young stars, and further still, the arms of the Milky Way. To cross the galaxy, a disk 100,000 light-years in diameter, is a project for a civilization that has mastered time itself. But even the galaxy is an island. The gulf between galaxies is the true void. Andromeda is 2.5 million light-years away. To cross that abyss requires speeds and energies that dwarf interstellar travel. It is a journey that spans evolutionary timescales. If humans ever reach Andromeda, they will not be the humans who left the Milky Way. They will be something else entirely, evolved or engineered to survive the Great Dark. So, how far can we actually go? The answer is a function of time. If we accept the speed of light as a hard limit, the reachable universe is defined by the human lifespan. At sublight speeds, we are confined to the nearest stars. If we master hibernation or generation ships, we can reach the breadth of the galaxy. If we transcend biology and become machines, we can reach the local group. But the cosmic horizon stands as the final wall. We can never catch the galaxies fleeing from us in the dark energy expansion. We are bounded, but the boundaries are vast. The reachable volume of space contains billions of stars and potentially millions of habitable worlds. It is enough. The limit is not a suffocation. It is a challenge. The universe has given us a sandbox of unimaginable size, walled off by the speed of light and the expansion of space, but filled with enough mystery to occupy us for the lifetime of our species. We are stepping off the ledge, and while we may never touch the infinite, the distance we can fall is deep enough to consume us forever. The journey is the destination, and the distance